So welcome today to the Picture Language Seminar. It's October 13th, 2020, and we have upcoming some interesting talks by Jos Slingerland next week, then Sebastian Talcou, and Liang Kong the week after that. And you can see on our seminar page the rest of our schedule. Today, we're really happy to have Xun Gao. He's a postdoctoral fellow at Harvard. He got his PhD in Tsinghua University in 2018. He was a student of Luming Duan, and afterwards joined the group of Misha Lukin at Harvard, and now he's jointly with my group as well. Today, Xun will talk about fractionalization, exactly soluble models, and quantum circuits. So Xun, why don't you share your screen?
Okay. Thanks, Arthur, for the introduction. Hello, everyone. Today, I'm going to talk about our recent work, fractionalization of quantum circuit and exactly solvable models. And this work is done with Yunxiang, Shentao, Zhengwei, and Arthur. The motivation of our work is trying to open the black box of tensor network. Here is an example of tensor network. The tensor network is defined on the graph, and on each vertex, we have a box which denote a small tensor. This small tensor has some indices which is associated with the edges around it. And the value of the this tensor network is defined by the product of those small tensors. And if there is an edge connecting two boxes, then the corresponding index should be summed over. For example, between A and D, we have edge labeled by K, so the K will be summed over. The tensor network has a wide range of applications, including quantum many-body physics, counting complexity, and even machine learning. And today, my talk only focuses on the tensor network representation for quantum circuits and partition function of many-body systems. Although we can draw the tensor network in a graph, in a picture, however, much of the information we cannot read from the picture directly. For example, those small tensors behaves like black box, which means the information for each box is hidden in the numerical values of each small tensors. And then I can give an example to illustrate what do I mean by open the black box. So let's consider the 2D Ising model. For the 2D Ising model, we have spins living on each vertex in this lattice. And if there is an edge between the two spins, then there should be an interaction between them. And the interaction we consider is the interaction with respect to the Z2 symmetry. And now we consider the partition function of this Ising model. This Ising model, we want to show that we can define a tensor network such that the value of the tensor network is exactly the same as the partition function. So the tensor network is defined in the following way. So for each edge, we can define a tensor with two indices, and this tensor represents the weight of the two body interaction terms. And for each vertex, for each spins, we define a tensor like this, which has four indices, and this four indices tensor, we can call it as copy tensor, because according to the definition, if we fix, for example, the index A to be 0, then all of the remaining three should be also 0. If A is 1, then B, C, D are also 1. So it copies the value of one of the indices. So we have 4 copies because one spin is involved in 4 interaction terms. Now we combine those tensors together, we will get this tensor network. And it's easy to show that this tensor network is precisely the partition function of the 2D Ising model. However, it's very hard to answer the following questions from the picture of the tensor network directly. For example, why it is exactly solvable, and why it is could be reduced to free-forming through Jordan-Wegener transformation, and how to understand the Kramers Wannier duality from the picture. So from the picture of tensor network, we cannot answer those questions. However, we will adopt the idea of fractionalization. We want to fractionalizing the spins of the indices in the tensor network. And then through the fractionalization, we can see the inner structure of lines and boxes in tensor network from picture directly. And there we can open the black box. And then we can understand these three questions through a very intuitive way. So our idea starts from, the starting point is the Kitaev's honeycomb model. In this model, it is a spin model, and but one spin is encoded as 4 Majorana modes. This is an idea of fractionalization. And then the corresponding spin models can be mapped to free-forming models, thus exactly solvable. So we want to ask the following questions. Can we generalize this approach to a general tensor network? And this is an exactly solvable model. Does it has a connection to other solvable models in statistical physics, quantum information, and computer science? And the answer is affirmative. We can extend this approach, then we can define some pictures, diagrams, such that we can open the black box of tensor network and in a topological way. And we can also understand 2D Ising model pictorially, and including understanding Yang-Baxter equation, Jordan-Wegener transformation, and Kramers Wannier duality. And then using this approach, we can generalize Kramers Wannier duality very straightforwardly, and then we can define some new exactly solvable models. And as a bonus, we get a unified framework for classically simulable quantum circuits, including Clifford circuits and Matchgate circuits. And also we can get their generalizations. So for one qubit or one index, we can regard them as a qubit. We basically use 4 Majorana modes, also 4 Majorana modes to represent one qubit. And we pair the Majorana modes in this way, pair the first and second one, third and fourth one. Then we will get qubit 0. And this cap can be understood as a ground state of Kitaev's Majorana chain in the topological physics. And actually it has 2 ground states. One is like represented as this and this. The Fermi parity is even, and it also has another ground state represented as this figure. And we have drawn a dot here to represent one charge, which means the Fermi parity should be odd. And this is also a Fermi parity odd ground state. And we also use two Kitaev Majorana chains to represent them. And basically, roughly speaking, we use 4 Majorana modes to represent one qubit. However, we are constrained to this subspace, which means the total Fermi parity should be even. So this encoding is known as Quon language on Z2, or also known as sparse encoding for Majorana 0 modes. And then as an example, I give some figures to show how to use this idea for tensor network. But so far, these figures might not make sense, but the goal of the rest of the talk is going to make those figures, the meaning to be clear. Okay, as an example, we start from Ising model. So for each line, which carries 1 qubit information, so it can be represented in the pictorial language we are going to use. We will use a tube to represent one line. Inside the tube, there are 4 strings. And there is a white circle. This white circle encodes the information of the interaction strength and temperature in Ising model. And so this is a 4 indices tensor. We basically have 4 tubes, and we glue them together and pairing the Majorana modes in this way. This represents the copy tensor. And when we glue them together, we will get a lattice, but the lattice is a lattice for some cubes. So it is a 3-dimensional manifold. And inside the manifold, there are some strings. Here, I use this notation to represent the genus in this 3-dimensional manifold. And this red color line, I label the most outside lines in those tubes in red color. So yeah, this is basically a way to draw the 3 manifold, those tubes into a 2-dimensional plane. And later we will show that once we have a genus and a loop around it, we can basically remove it. It's a constant. This is called string-genus relation. And then we can reshape the diagram after removing genus. This is the original shape, and we reshape it to this shape. And later we will show that if there is no genus in a diagram, it basically represents free-forming. And then we can add string-genus relation at this position. And in summary, we start from the Ising model represented in this way, and then we shift the position of string-genus relation to another position. We will get a new model. And we can show that this new model is basically the Kramers Wannier duality, the model after Kramers Wannier duality. So roughly speaking, the Kramers Wannier duality is nothing but shift the position of the string-genus relation. And then we can generalize the idea to some new, more complicated cases. Here we have a free-forming, and we have some string-genus, but this string-genus is more complicated. It is nested, and we can put them together to get this figure. This figure can be interpreted as a tensor network. It can be understood as a partition function of 2D Ising model, but with magnetic field. And we can also understood this as some many-body system involving interacting fermionic terms. And we can even consider a much more complicated one. So far, those figures might not make sense, and the rest of the talk is going to make it clear. Okay, the outline of the rest of the talk. First, I will summarize the pictorial rules from the sparse encoding of Majorana zero modes. And then we give a topological characterization of Ising model of planar graph without magnetic field. And we can understand star triangle relation, Jordan-Wegener transformation, and the Kramers Wannier duality through the picture. And then we can define new solvable class as we just saw. And we can generalize the Kramers Wannier duality in topological way, and we can define some non-trivial exactly solvable models. And we also have some other applications, including a unified framework for Matchgate and Clifford circuit, and we can also generalize them by combining them in some topological way and find some algorithms to evaluating those circuits. It is a way much like untying knots. And we also give a representation which is suitable for coding, and this might be useful to do quantum circuit compiler. Okay, with
when you mention without a magnetic field, do you just mean a classical Ising model?
Yeah, classical Ising model, or 1+1D quantum Ising model.
But that has a magnetic field, so. Yeah.
But it's not a generic magnetic field, but magnetic field followed by some patterns. Mm-hmm.
Thank you.
Yeah, the basic rules. Here I draw the 2 ground states of Kitai's Majorana chains, and it has 2 ground states in the topological phases, and the only relevant Majorana modes is the first and the last modes. So the ground state is labeled by these operators if the operator is +1, which means the Fermi parity is even. If it is -1, the Fermi parity is odd. So we draw a dot here, a charge here. And then after removing the irrelevant part, and we can abstract the diagram in this way. We have 2 caps and to encode some qubits. And then when we draw a line straight vertically, which basically represents the word line of the extreme point of the Majorana chains. And if we have a charge here on the first mode, which represents the gamma1, the Majorana operator for the first mode, this is gamma2. And these 2 figures basically represent the commutation relation of Majorana operators. And then we can also define the Fermi parity operator. And we basically draw the two charges at the same horizontal line. And we can understand which is equal to I times gamma1 and gamma2. And we can understand this phase I through, because if we exchange the position, we will get minus sign. However, we basically have a half exchange, so we have an I phase. And we can also move the charge from left to right, but we also have a sign I. And this can be understood in this way. We can imagine the charge is a Fermi, and when we move it from left to right, it basically rotates by 180 degrees. So we have a phase I. So using these rules, we can derive this equation, which basically means if we have 2 charges at the same time, and they basically equal to the vacuum, because we can create a pair of Majorana fermions from vacuum. And this equation, we can also understood this as a definition of the first ground state, because it is the eigenstate of this operator. This operator is basically shown here. And then we can represent vectors, and we can also represent dual vectors. Then we can compute the inner product, and then we can define we can find some rules, like we have a loop, and if there is no charge, which is a constant, this constant reflects the quantum dimension of Ising or Majorana zero modes, and we can also the inner product between 0 and 1, we have a loop, but with a charge, this will be 0. And we can also define the braiding operator. The braiding operator is for Majorana fermions, and it has this effect. Basically means we can transform gamma1 to gamma2, but transform gamma2 to minus gamma1. So this rule tells us charges can almost freely move up to some phases. And using these rules, we can derive that we can basically exchange the order of the braiding, but the cost is that it will produce 2 extra charges. And then we also have some isotopy relation or relativistic moves. We have those rules because we can imagine these strings as a word line of the extreme point of the word line of Majorana zero modes. And those makes the diagram behaves like a knot, but actually it is easier than knot, the ordinary knot, because we can see that we can exchange the order up to some almost freely moved charges. So every diagram can be reduced. Each diagram is basically the trivial links. And then this is, we can define an operator like this, a white circle, we call it as parameterized crossing. It can be defined as superposition of 0 charges and 2 charges. And here, they can written as this form. In the exponent, we have quadratic term for Majorana operators. And basically, we can see this diagram. We have we have quadratic term for the first and second and third one. They basically represent the spinor representation of SO2 SO3 SO3 group. And here it basically represents the Euler decomposition of a SO3 rotation. We have two different ways to do the Euler decomposition. So we will have this equation. Notice that we should update the parameters in each parameterized crossing. This is basically the Young-Box equation. And then let's go to the sparse encoding of Quon. We will use formal random mode. And notice that all of them will have even number of charges. And here this is the different way to pair the modes. And this is the basis for poly X operator. This is basically for poly Y operator. And why this is poly plus state is the eigenstate of poly X operator, because we can simply compute the inner product. We will find it is indeed plus state. And then we can also represent poly matrices. This is basically the Kitaev encoding of poly operators, because we are constrained to this even parity subspace. Using diagram, it is represented as this. And notice that for poly Z, we have two charges on the first two strings, and X has two charges in the second and third strings. Later we will use it to represent any SU2 matrices. And we can also give the S operator, which is called phase operator, which is basically the braiding between the first and the second or the third and fourth. This is some can be derived using the property of Majorana zero mode, and also Hadamard matrices. The Hadamard matrices, we can simply verify it. When we apply Hadamard matrices to 0 using the Reidemeister move, we can get plus state. And if we apply it to one state, and we can move the charges, and we can use Reidemeister moves, then we can get minus. So it's indeed Hadamard. And notice that because we are using sparse encoding, it has some redundant degree of freedom. For example, if we have two braidings that are basically equivalent to identity, we can verify it by apply it to 0 and 1 state. So on the basis, it behaves like identity, so it's indeed identity. So later we will show that this rule is very important for evaluating Clifford circuit. Then we
could I ask a question?
Sure.
For the Hadamard, how do I see that it squares to 1? Because it seems like the first one, if you apply twice, it gets into the third. Like in your, like first gets sent to the second one, but how do I see that Hadamard squares to 1?
We need to use, actually we need to use this redundant degree of freedom. You cannot it directly.
I see, thank you.
So we can also represent SU2 because the first two, if we have superposition for first two strings, we basically represent this rotation along the axis. Then this is for x-axis. We can do the Euler decomposition for SU2. We have other ways to do it due to the redundant degree of freedom of this encoding. Then we have already introduced all the single qubit operations. Now let's consider multi-qubit operations. Let's start from Control-Z gate. The Control-Z gate here, I just adopt the protocols from this paper. At the first step, we measure the fourth and the fifth modes under this operator to be +1, and we already see that this is represented as this, simply a cap. And then we braid the mode 3 and mode 6, and then we prepare a state on as the eigenstate of this operator. We know that this is simply a cap without charge. And the fourth step is very important because we are using sparse encoding. We need to make sure each four strings in one group should have parity even. and also for the sect groups. So we need to mirror the parity to make sure the parity is indeed even. And then we do the two braid, then we will get Ctrl-Z operator. So in general, for a general tensor network or two-qubit gate represented by tensor network, the way to draw them in the fractionalization way is the following. We need to draw a tube to group each 4 strings together. For example, for each line, it is a tube, and inside the tube, there are 4 strings. Why we draw a tube? The tube is the rule of the tube is to remind us we need to make sure the parity should be even for these 4 strings. And then, for a general tensor network, we basically enhance each line by a tube, so we will get a 3-dimensional manifolds. So we will have genus. A convenient way to draw the figure is to draw them in a 2D plan. So we simply use this notation to denote the genus. So we need to make sure between 2 genus, we have 4 strings. If we have 4 strings, we need to make sure the parity should be even. Now I will give an elementary objects, which is useful to construct any 2-qubit multi-qubit operations. We call it as copy tensors because we can regard it as this as input and those 2 are as output. If we have 0, then we have 2 copies 0, and if it is 1, then we have 2 copies of 1. So our other assignment with indices should be 0. And then we use this diagram to represent identity operator. Copy tensor. Why? Because we can simply verify it by contracted with qubit 0 and 1. And here we start from 1. And we know that in order to make it non-zero, this loop should have charge number to be even. So there is no charge here. And similarly for this loop. And this is simply a loop. Then we know that this is 0, this is 0. So it copies 0 to 2 zeros. If we start from 1, and in order to make the number of charge to be even, we need to have a charge here. And similarly for this charge. However, we know that in each tube, we should have even parity. So we can prepare a pair of charges from this vacuum, and then we will get 2 extra charges. So in this case, we copy 1 to 2, 1. Then we can glue a copy tensor and Hadamard tensor together to define the Ctrl-Z gate. We can simply verify this tensor network. We can regard the left indices as the left 2 indices as the left index of a matrix, and similarly for the right 2 indices. And after direct calculation, we can show that this is the matrix representation. It's indeed Ctrl-Z. Then using the copy tensor and the Hadamard tensor together, we get a Ctrl-Z operation drawn in this way. And we use the redundant degree of freedom to move this braiding to here. Then we just move them from here to here, from here to here. We will get this exactly the same diagram as we shown before. Okay, so the genus will prevent us to freely move the strings. Notice that if there is no charge, those 2 diagrams should be equal. However, there is a genus we cannot freely move because we can, for example, we can consider this configuration. We have 2 charges on the left and no charge on the right. If we have this diagram, we can move the charge from here to here. Then at this time step, we can see that in each tube, the number of charges is odd, which validate the parity even constraint. However, sometimes we are lucky to have this configuration. This will happen when we consider Ctrl-Z square. I will not give the detail, but if you do the calculation, you will find this configuration. And we have a charge genus, and we have a loop around it. And in this case, this can be understood as prepare a state and then mirror the state to itself. And it seems that it's not simply nothing, so we can remove it. However, we want to make sure at each time step, each 4 strings must have even parity. So in this case, it has even parity. However, what if there is a charge here, there is a charge here, then we can basically notice that the total number of charges is conserved. So if this is odd, this is also odd. Then we can prepare a pair of charges from vacuum then to balance the parity aside the genus. So roughly speaking, so far we can, once we have this configuration, this called stringenous relation, we can remove it because it is a constant. And for rigorous proof, people can refer to this paper. And then I can give an example. I mean, if we cannot simply understood as we have prepare measurement process, then we can remove it. We cannot do it actually. Because suppose we have this process, we prepare a state from 4 modes and then mirror it into this state. However, we cannot remove it because let's consider the second case. And in order to balance the parity, we need to prepare a pair of charges. And when we move the charge, we will find that they will not be canceled. So which means for the first case, there is no charge in this diagram. For the second case, there will be some charges which cannot be eliminated. So the 2 diagram is different. So we cannot use a single diagram to represent this case. So we cannot remove this configuration directly. Okay, in summary, we define some basic elements. Qubit, poly, single qubit Clifford, and other single qubit operations. And for multi-qubit operations, we need to involve genus, and we can define copy tensor. And notice that those elements are universal to represent any tensor network. We basically enhance the lines in the tensor network to a tube, and this tube we have 2 strings inside. Then we have some pictorial rules, including the as topping move. They can be understood as word line of Majorana 0 modes, and also how to remove charges, how to move charges because according to the rule of Majorana affirming, and exchange the order and breeding, and also loops with or without charge, and redundant degree of freedom, and stringenous relation. So those rules are very powerful, which enhance the power of fractionalization, and later we will see, especially the first and the last rules are very important. Okay, then as an example, let's discuss how to apply this approach to the Ising model. We basically want to understand Kramers Wannier duality, star triangle relation, and Jordan-Wegener transformation. This is a tensor network, and we have a copy tensor and the 2 indices tensor for interaction. And this is copy tensor, and the fractionalization of copy tensor. Then this is for the interaction tensor. And we can glue them together for the tensor contraction. We will have this diagram. Then we have a stringenous relation. We can remove it. And after removing all the stringenous relation, we will basically get a diagram without genus. And if a diagram, there is no genus in a diagram, it's basically a free-forming, because according to the definition of this parameterized crossing, it is basically a quadratic, the evolution of quadratic terms for forming operator. And then for Kramers Wannier duality, this is for the original Ising model, and we can shift the position of stringenous to another places. And we will get 2 models. And this model is defined on the dual lattice of the original model. And for the interaction term, we have 2 interpretations. One is the interpretation from horizontal direction. So we can write it in this way, according to the definition. Then we can also understood it through the horizontal direction. which is equal to this. This can be computed from the fact that we remember that we define the qubits by pairing 4 Majorana modes. And if we have different pairing, we basically change the basis from, for example, 0 to plus. So we can basically use the 0 and plus state, and we will get those coefficients. So this is exactly the Kramers Wannier duality. So in summary, what is the Kramers Wannier duality from the perspective of our picture language? It's basically nothing but Ising string genus at different positions. Then let's consider another relation transformation called star triangle relation. And this is a star configuration, and we can use the copy tensor and the interaction tensor. We can draw this figure. Then we already see that we have Yang-Box equation from the Euler decomposition perspective. We can move these strings from the here to here, then we will get this diagram. Then we simply reshape the diagram and put a string genus relation inside it. Then we can find that it's simply the triangle triangle tensors. Then how about Jordan-Wegener transformation? The first line is basically the Fermi operator. And then we can add some blue and some ancillary strings colored by blue. In the middle, we can use string genus relation. Here, I just draw half of the string genus relation to introduce the ancillary strings inside the block. But on the boundary, we always use 2 extra strings. And for gamma 5, notice that we can represent the even charge, the total charges to be even. So we add a charge on the most left as a reference charge. Okay, so then we have a gamma 5 here. Notice that we need to make sure each 4 strings should be even parity. So in order to balance the parity, we can prepare a pair of charges. Then here we will get 2 charges, which corresponds to the poly Z operator. However, here we have an extra charge. In order to balance the parity, we do the similar trick and we prepare a pair of charges. And here we have 2 charges which define the poly X operator. Now this is poly X. So gamma 5 is equal to Z times X times X. So this is for gamma 4, and we can use the same trick and to prepare the parity, and we'll get XY, or Y times X. Now here is an example for gamma 4 and gamma 5. We can prepare a pair of charges, then the parities are conserved, are even, and then this corresponds to poly Z operator. So the Jordan-Wegener transformation from this perspective is nothing but simply create a pair of charges around the genus. So when could we reduce a spin model to free-forming? It's simply in the case that we have locally removable string genus relation. Then we can use this approach, generalize the idea of the discussion for Ising model here. And we know that once we can remove some genus through string genus relation, we can reduce the model to free-forming. And then in this case, we can basically have 2 layers of diagram. The first layer labeled as red color. The second layer is the black color. And the black color part, there is no genus, which represent free-forming. And the red color part, we have a nested string genus relation. For example, here, we have a string genus, we have a loop here. We can shrink the loop around the genus, then we can remove the genus. Then we will get a loop here, shrink it, remove this genus, and so on and so forth. We can remove this row. And similarly, we can remove this row, this column, and this row. Then we will get a free-forming model. But notice that it is quite different from the previous Kramers Wannier duality. In that case, we can remove all the string genus relation at the same time. However, in this case, we need to do it sequentially, and also those string genus relation is not non-local. We need to shrink it to a loop around the genus and then use the string genus relation. And we can even use even create more complicated cases as this one. And one thing I want to mention that when we have locally removable genus, actually it can represent some interacting forming terms. As an example, I draw a figure here, and according to the pictorial rules we introduced, we can show that it is equal to a quartic terms for Majorana operators. So it is interacting forming. Okay, now let's discuss other applications. Here I will be quick because our folks, we basically, today the talk is basically focusing on the Ising model and the generalization. The other applications, including basically including the result from quantum circuits. So now let's consider a quantum circuit called Matchgate circuit. I will give a definition later, but we can start from the people may be familiar with the diamond models. But this is a diamond models, which means we have a graph and we want to define some dimer. Dimers is labeled as a blue color, which occupy two vertices. Then the diamond model is basically that if we consider the zero temperature partition function, we basically want to count the number of configurations such that each vertex is occupied and only occupied by one dimer. And this counting problem is also called counting perfect matching problem from computer science, which can be defined using those tensors. These tensors have three indices, and it is one if and only if there is one index to be one and others should be zero. This is also called W state from quantum information community. Why we have this tensor? Because if it is one, we basically have a dimer in this edge, and each vertex can only be occupied one dimers. And also we can generalize it by introduce some weight for each edge. The weight can be different over different edges. Okay, we have these two tensors. We can represent fractionalizing them using our picture language. And it is drawn here. I will not give the duration, but simply give the result. It is drawn here. Here we use plus minus basis. And the parameters in the white circle is pi/3. And this is for the weight. And then we can glue them together. We get the value of the tensor network is simply counting the number of dimer configurations. And we will get this diagram. Notice that we have string genus relation. We can remove them. Then we can reduce this problem to free forming. And in summary, a Matchgate tensor or quantum circuit is basically those can be composed of the above two kinds of tensors on planar graph. So we already see that, notice that the boundary string does not interact with the strings inside the block. And inside the block, there is no genus. So we have a characterization of a Matchgate through our picture language. As I just said, the boundary cannot breed or interact with other strings, and there's no genus inside. So this is a picture characterization of Matchgate tensor. And using this, we can also apply the Young-Box equation and other rules to give an algorithm to evaluate Matchgate tensor. Matchgate tensor, after removing all the string genus relation, is basically a free forming model, and which can be shown like this. Notice that for each crossing, we have some parameters. We can derive this equation is simply like we apply this theta to 0 and we get nothing. So we have this equation. We also have this equation, which basically reflects the fact of this equation. And also the Young-Box equation, as we mentioned, from the Euler decomposition perspective. So we basically have a modified version of Reidemeister move. Notice that the second one is different from the ordinary Reidemeister move. Then we can apply those rules simply that we can always find a configuration like this, and inside this red region, also inside this region, we have some other strings. We can apply the Young-Box equation to move them outside this region, and then we can apply the second one to reduce the number of crossings, breedings. Then we can keep doing this. Then we can evaluate the tensor network of Matchgate. And then we can also discuss Clifford circuits. Clifford circuits is composed of Hadamard, Fishgate, and Pauli, and copy tensor, because copy tensor and Hadamard can represent Control Z. And the pictorial characterization, we already say that, which is basically the diagram without parameterized crossing. We can have breeding, genus, and charges. And we can derive these two equations for tensor network through untying some, using the Reidemeister move and stringiness relation and the redundant degree of freedom. And applying this rule, we can derive this a transformation called the local complement for graph state. And using this local complement, we can evaluate Clifford tensor network efficiently. So in summary, we have a unified framework. If we only have genus, breeding, and charges, we can represent Clifford. Actually, we can use those diagrams to derive ZX calculus. And if we without genus, we can define Matchgate. We can use Matchgate, those diagrams to derive rules in ZW calculus. Then we can also combine them together in some specific way, a topological way, as we see. It's basically, we can define some new, as we see in in generalizing Kramers Wannier duality. So we can basically define new solvable classes of quantum circuit. And so in the generalization of Kramers Wannier duality, we basically have nested stringiness relation. And because they do not have parameterized crossing, so it's simply a special case of Clifford. So which kind of Clifford do we have? So actually, we can extend this nested stringiness relation to 3D, not only for 2D, but in 3D, which types of Clifford can be viewed as nested stringiness relation? It is those Clifford which can be evaluated or simplified without using these rules. Then in this case, it's a nested stringiness relation, even for 3D. And the knot seems like it is a continuous object, but actually we can we can represent it as a discrete object in the graph. The idea is using the media graph. Consider a knot diagram, and we consider the shaded projection. Then we can define a planar graph by associating each shaded faces as a vertex, and if there is a breeding between two shaded regions, then we can have an edge. And oppositely, starting from a planar graph, we can always define a knot diagram. And then notice that sometimes we have genus, sometimes we do not have genus. So we basically have two types of vertices. And also, because there is parameters on each breeding, so we need to assign parameters for each edge. So then we can show that for all the pictorial rules, it can be represented as transformation between the planar graphs. For example, this is a star triangle relation from the Young-Box equation. Notice that we have genus here. All right, so that's all I want to discuss. I can give some summary. So first, we apply this approach to Ising model. We understand it, Kramers Wannier duality, Jordan-Wegener transformation, and the Young-Box equation. It's nothing, but it's simply locally removable string-genus relation. Then we define new solvable classes by generalizing the Kramers Wannier duality in a topological way. We just combine preforming part and nested string-genus relations. And the interpretation can be Ising model with magnetic field, and because it violates the condition of Matchgate. And also it can also be understood as interacting forming operators. Then we also give examples for the application of quantum circuits and define using media graph to define representation suitable for programming. So the outlook, we hope that we can, for example, we can apply the media graph representation to design a quantum circuit compiler, which might be useful for simplifying quantum circuit. And we also hope that we can also ask, could we apply the general framework of the generalizing Kramers Wannier duality to find some new exactly solvable model, but with some physical implications. And also we discuss Matchgate and counting perfect matching, and we are curious about whether the new solvable class can be used to find polynomial time algorithm for some new combinatorial problems. And we also have these new solvable classes, we can also regard it as variational ansatz. And this might be powerful because we accept the Gaussian Fermi part. Gaussian Fermi basically means free Fermi. We can also introduce the non-Gaussian part. Non-Gaussian means interacting Fermi term. So, but at the same time, it is still efficiently computable. So maybe this ansatz has potential application for example, quantum chemistry. And more theoretical questions, could we extend this idea, the fractionalization idea, to some other annual models and different encoding ways? And actually, so the sparse encoding for paraforming has already been discussed in Quon language for ZD cases. Yeah. Okay, so thanks for your attention, and thanks for my collaborators, and also thanks for Xun Wan and Fernando for insightful discussions. Yeah, thank you. Yeah, that's all.
Well, thank you very much, Xun, for a really interesting talk. It's more physics type talk than many of the others, but it has so many nice ideas.
Thank you.
So I'm sure there are many questions.
So can I ask a question? Yeah, thanks, Xun, for the beautiful work. So, I mean, I think like I have a lot of questions, but I discuss with you later. But maybe also regarding some of the outlooks that you put. So I think one interesting thing maybe to look at, I mean, like maybe to ask a question is that how, if we consider a Hamiltonian that might have like disorder, that the J's are not like in your Ising model, if the J's like have some disorder, would you be able also to sort of like have a similar pictorial representation, or how you can compute actually the partition function for that regarding, but I don't know.
Yeah, for generic disorders, we cannot do it because the computational complexity is hard. But here it's definitely efficient in polynomial time. But once they have some hidden topological patterns, I don't know how to define it in terms of the ordinary spin Ising model language, but there should be some characterization. We can do it. We can also introduce disorder because here on the parameterized crossing can be arbitrary parameters. And you can also notice that the shape can be also very complicated for the nested string-genus relation. Yeah. maybe we can define a class of disordered system, and it can also be solved.
Yeah.
Yeah.
Sure. Yeah, let's talk about it. Yeah.
Sure.
But then also, like, I mean, like, as far as I understood, also this formalism, you can still, like, how is going to change when you are actually close to the phase transition, when you actually go to continuum limit? Still everything would be valid, I think?
For example, suppose we consider the partition function e to the power minus beta h, and if we consider in this way, h is quantum Hamiltonian. So far, I don't know how to represent it because we basically use some characterized version of partition function for quantum Hamiltonian. But when we take the continuous limit, I don't know how to tackle this problem.
Yeah. I mean, you literally write up some like action, but I don't know exactly like how you're gonna, like how it's gonna happen. Yeah.
Characterized version.
Yeah.
So are there other questions?
Hi, I also have a question. Yeah.
Who's talking?
Xing.
Oh, me. I'm Chining. Yeah. Hi. Thanks, Xun, for the talk. Yeah. So since I'm from a CS background, so my questions might be a little bit vague. Yeah, and unprecise. But I'm wondering, like, so in theoretical CS, we can show that like in general, counting perfect matching is sharply hard. Yeah, I'm wondering, this kind of like hardness, like reduction result, can be also phrased in this kind of Quon language. Yeah, like basically you use this language to prove easiness. Yeah, like can be solved in polynomial time. Yeah, but can this language also be used to prove some hardness?
Yeah, sure. For example, as you mentioned, the counting perfect matching for a non-planar graph, we can basically represent we can represent a diagram without a string genus relation. We have many genus, but they cannot be removed. Then in this case, it should be hard. But whether it is sharply hard or NP hard, we don't know how to get the sharply hard from this. But we know that it is hard if we have many irreducible genus.
But this is hard in what sense? Like,
yeah, actually, hardness is rough. Usually, we use those problem to construct some gadget to represent other known hardness problem, which is hard, right? What that basically means that if we allow to use non-planar graph using these two tensors is for perfect matching, right? And we can basically represent universal quantum circuit, for example. But it's much like simply constructing gadget to represent a known hard problem. But maybe we can reformulate it using diagram without writing the formula.
thank you.
No problem.
I have a question. This is George Siapsis. If I understand correctly, you're using a definition of control Z that's probabilistic.
Oh, yeah. So here we only consider post-selection. Actually, we only consider one branch of the measurement results. If we have other measurement results, we will get some extra charges, and we need to apply other charges to correct them. But the resulting diagram should be the same.
But it's a probabilistic definition. I mean, you have a measurement up there.
Yeah. Well, so yeah, actually, this is not precise. Basically, we are using post-selection. We can get one measurement result.
You're probabilistic. which is not good in general. But my question is, there is another definition I thought that's not probably, it's deterministic. It involves only braiding in the Ising model. Isn't that right? Have you considered that definition?
Does it use different encoding?
Yeah, I mean, different from what you have.
Oh, we haven't considered it.
Okay. Because things will change one day, if I understand correctly.
Although the protocol is probabilistic, but what we need is only the diagram. I mean, here I just give the correspondence between the operational meaning, but actually this is simply just some abstract diagram. So we do not need to consider probability.
Well, you do if you do an experiment.
Yeah. Here we just use it to do some mathematical derivation instead of.
Yeah, but if you want to connect with an experiment, it becomes probabilistic. I mean,
Yeah.
That's what kills it actually, because if you have 100 of them, then the probability becomes so small that you cannot. The circuit is not useful anymore.
No, but we can do some local correction. To do this, I mean, suppose we have some.
But there is braiding. I mean, there is a definition with just braiding.
Oh, yeah.
So anyway, I can talk to you later, maybe.
Yeah. Thanks for your suggestion. We can have a look.
Are there other questions? Well, if there are no other questions, I'd like to thank Xun again. And that was really a nice talk, full of many ideas, and we'll look forward to the papers. So thank you.
Thank you, Arthur.
See you next week.
See you.
Bye-bye.
Bye.